Hello all, welcome to the most comprehensive guide to alternate propulsion and exotic propulsion technologies. And then we just need to cover what is propulsion, right? Propulsion is, if defined by Newton's law of motion, to every action there's equal but opposite reaction. So if you have a water hose, for example, high pressure water hose, water goes out one way, the hose goes the other way in haphazard manner in proportion to the water that's the ejection mass. When you have a rocket, for example, you have a high pressure explosion or rocket exhaust going one way, and the rocket goes the opposite way. Now, how does it work in a vacuum of space? There's no oxygen, right? That's the question. How does rockets work in the vacuum of space and there's no oxygen? It makes no sense. Well, in the rockets, you have oxidizer, which is liquid oxygen. Notice, and you have propellant, which is the fuel. Notice when you put a glass over a candle, it snuffs out the oxygen, and the fuel, which is the fuel for the fire, for the candle to continue burning. So this is how rockets operate in the vacuum of space. I have a little sloppy analogy for it here. So the exhaust here, this is my handwriting that should really need it, goes one way, and the rocket goes the other way. And this is the oxidizer tank, and this is the propellant tank. They mix together in a chamber, and it explodes in a controlled explosion, which, if you're not careful, you have combustion instability, which is an explosion so unstable it causes the whole rocket to go boom. Right? So that's not exotic propulsion technologies, but that's just propulsion technologies that we know of. Then you have ion thrusters. All ion thrusters is a charged gas propelled by magnetic fields through an exhaust nozzle, and its thrust is very low, but a specific impulse, how fast each atom of whatever gas, xenon, is coming out. You know what I'm saying? So how fast it's coming out. So picture it like this. You can have a lot of atoms coming out once, but coming out really slow. That's your thrust. And an explosion. And that might get you so far to run out of fuel. It's a lot of how much stuff comes out. This is how fast the stuff comes out, but you only have a little stuff coming out, which is the atoms. This is responsible for your top speed. This is responsible for how fast you, how quickly you accelerate. So the thing is, for xenon, for example, ion thrusters, if there's nothing acting upon it in the vacuum of space, it's like it has the thrust of a piece of paper constantly stacking on top of your hand until the force is tremendous, the weight is tremendous of the thrust, the accumulated specific impulse, until it goes 100,000 miles per hour in the vacuum. This is a whole bunch of paper coming out at once, but it doesn't have the accumulated momentum as this down here. So forgive me, that was a sloppy analogy. But think of this as instant bursts of power. I think of this as incredible momentum. Okay. So the ideal situation between the two, between a rocket engine and the ion thruster, is to have the high momentum of an ion thruster, the high top speeds, how fast the atoms come out, with the high thrust of a rocket engine, without the fuel running out every 7 minutes, 10 minutes, 20 minutes, however long it lasts, which is usually nowhere near as long, almost never basically never nowhere near as long as the ion engine. The ion engine is used in the Dawn spacecraft for high velocity propulsion. High speed and velocity. Velocity is basically momentum of magnitude and direction. Which is a vector property. Vector is magnitude and direction. How immense the velocity change, speed and direction, and stuff like that. So now what? So those are two forms of propulsion right there. So then you have, say, Einstein's E equals mc squared. I know you can't read my handwriting. I showed it to my time. Einstein's E equals mc squared. Where is this up here? E equals mc squared. So why is that important? Energy equals to mass and the speed of light of a vacuum squared. Okay, so all it's saying is you got stuff. Let me see. Give me a second. What I got right here for this? He's got this muffin, right? This is mass, and it gets burned into energy. See, it's a pure form of energy, and that energy and the mass. Imagine a ball of light, a blueberry muffin. Ball of light, which is energy of this blueberry muffin, converted by antimatter properties, right? I say antimatter, but it can be nuclear, which is less efficient than antimatter. By like, nuclear is only 1% efficient, or you could just set the whole thing on fire. It's stupid, but I'll set that muffin on fire. But it's the conversion of every molecule, of this into pure energy, right? Let's see. Let me think here. So energy and mass is the same thing, right? It's just different forms. Energy, just like mass, can either be created or destroyed. Okay? All right? Boom. So they just changed form. So think of it as the same thing. So if I want to have an impression of mass on space-time. So what is mass on space-time? Mass on space-time is like a bowling ball on a Tempur-Pedic mattress. A bowling ball on a Tempur-Pedic mattress, right? That's its mass equivalent. And let's say the bowling ball is 8,000 miles in diameter. Let's say a bowling ball is 8,000 miles in diameter. And 14,000 miles, I'm tripping. 16,000 miles in circumference. So 16,000 miles in circumference. All right, 8,000 miles in diameter and 16,000 miles in circumference. That's your bowling ball. If you have a bowling ball that big, I hope not, it will make an impression on space-time enough to bend that space-time to where we feel one Earth gravity. Right, neither. One Earth gravity, which is the constant pull we feel. Downward pull, right? So, boom. Let me make sure I got this right here. If I set the song to me, nothing wrong. It's 9.8 meters per second. I was thinking 9. I forgot the exact numbers. 9.8 meters per second. Right? 9.8 meters per second of downward force. Right? So a famous NASA scientist named Charles Bueller came up with, he's semi-famous, came up with a electric propulsion method that can have or simulate one Earth gravity worth of force, which is enough to get you to Mars in probably like 3 days to a week, however you choose to do that. So this is a constant force that causes you to accelerate, which is 1, Earth gravity, or 9.8 meters per second. Now, I'll write meter, but I have to take my time. I'm writing slow. This video is going to last forever if I go too slow. So, 9.8 meters per second. Now, boom. We have this Earth sitting on space-time. Let's go back to it. Earth sitting on space-time. It's mass. If it's converted to energy, it's going to do the same thing. So you have the sun sitting on space-time, which is far more massive than the Earth. And it's the center of the solar system. Boom. See the sun sitting on space-time. And this is the fabric of space-time. That's the sun. Forgive my son. So you got something massive like that of energy. And scientists noticed that a star that's supposed to be behind the sun, a star that's supposed to appear behind the sun, slightly behind, appears beside the sun. And that's only because you have this bend in space-time created by the gravity or mass of the sun, which is the most massive object in the solar system. Probably about 98% of the mass in the solar system. So that's enough to warp space-time to make objects appear behind, slightly beside. That are behind, slightly beside. So what is space-time? What is this fabric? How does it work? It's dimensions that you and I see in, right? So you got, or exist in. So you got, boom. Say you got a line. Here, let me just use another paper. You got a line. That's one dimension. You got a right angle. So sometimes some of us take L's in life, like me, but that's the right angle. Now, you got a cube. That's 3 dimensions. Woo! That's what we exist in, inside the cube. Now, going from point A to point B inside this cube, going from point A to point B inside this cube, which is point A, point B. So you're going point A and point B inside space-time. That is time. Now, picture the Earth inside this cube. That is what we exist in. And Earth's impression inside this cube is space-time. So why is this important? It's important because we now know that if we have enough energy, and it can be any form of pure energy, right? We can warp space-time if we have enough of it. Okay, so antimatter, matter, collisions, whatever, it will warp space-time theoretically because we observe this in black holes. Black holes would create gravitational ripples as they orbit around each other, right? And what is those ripples? It's ripples in the fabric of reality. So, see, remember Spider-Verse, Spider-Man, I guess, right? So there's a famous physicist called Miguel Alcubierre. He said that if you could, using Einstein's theory, compress space-time in front of a vehicle, right, and expand it behind, that vehicle would move, compress space-time in front of the vehicle and expand it behind. That vehicle will move without moving, which is using gravity to propel the object, which is what the manipulation of space-time is, gravitational waves. So all this is that's propelling the object is G waves, gravitational waves. Cool. You feel me? We're tracking. And that's physicist Miguel Alcubierre warp drive. Cool. We're tracking. Miguel Alcubierre. Excuse my language. excuse my English. This is backwards. All right. So Miguel Alcubierre warp drive. Just have this. Say, hey, go, Miguel Alcubierre. I don't know what you're talking about. Warp drive. You know how to spell warp, right? So, boom. Why is this important? We know that black holes, supermassive black holes, create gravitational waves. Oh my God, that's horrible. Which is ripples. Supermassive black holes create gravitational waves, which is ripples in the face of the space-time reality, right? So that's basically propulsion all around here that we can use if we translate it into energy without creating a black hole and stuff, right? Which is basically a black hole is basically a tunnel theoretically going somewhere we don't know where it's going. In space-time, which is a wormhole. Don't worry about that. That's different. That's something different. We just got to worry about how to warp space-time around an object. Now, my theory is that because everything that has mass makes an impression on space-time, that means anything that has mass makes an impression on space-time. If you ascribe to the theory that anything that has mass makes an impression on space-time, then what do you do then? That means you can use something that has mass and manipulate it into a rotating mechanism. But you have black holes that are immensely massive. And how are you going to create the energy and enough energy that a black hole or the proportional equivalent of a black hole's worth of energy to warp space-time to create gravitational ripples on the scale of a human being's rated spacecraft, which is an ant compared to a Leviathan, or an ant compared to SeaWorld. That was a bad joke. So what we do here, there's a cat on the ground, see. So what we can do is, how do you, say you had an Earth amount of energy, a celestial body amount of energy compressed down to a cylinder, and then you have a larger cylinder at the bottom with an Earth amount of energy, right? Now, how would you, in effect, warp space-time with these energies to compress and then contract, right? All there would have to be, theoretically, is an asymmetry compared with these Earth's amount of energies. And there's an asymmetry with Earth, amount of energy, I'm doing it without looking, amount of energy, a small amount of energy on the top in comparison, and a large amount of energy on the bottom in comparison, that are fixed together without conflicting, and then make sure that the charge, like there's different charges in of atoms, there's positive and negative charges that cause them to interact. Make sure they're non-conductively attached in that manner, if I may use that terminology. So say you got positrons and antiprotons, positive charged electrons and antiprotons, negative charged, the opposite of protons and electrons, right? And this is antimatter, and it's enough for a celestial body. And on the top and bottom, let's say Earth and Jupiter. So boom, Earth and Jupiter. So boom, there's going to be asymmetry, and that will warp space-time, like the Miguel Alcubierre drive, and cause the spacecraft to go in one direction, right? So that sounds crazy. It sounds messed up. And we're going to get an Earth amount of energy Relax. Your boy got you. Okay, so I know, and a lot of you heard of Tesla, not Tesla car company, but Nikola Tesla. Nikola Tesla, who created alternating current and alternators and all that good stuff. I'm saying. So why is Nikola Tesla important? Because he has something called Wardenclyffe, which is a giant Tesla coil, where he experimented it on a electrically powered flying device. Now, this looks like BS, but electrically powered flying device. That was like a old fingernail. But anyway, so you have an electrically powered flying device. So how does it work? I'm glad you asked. So an asymmetric capacitor, if you heard of this and you looked at it on Google, is basically a charged plate, another charged plate, and a force, I don't know if you can see it, a force between these two charged plates, non-conductively attached, allowing for propulsion in one direction. Between these charged plates. It's a measurable force between these charged plates. Let's say this is for the heck of it, say one's positive, one's negative, and one has more positive charge than negative charge, right? So charged plates. Okay, so charged plates is a lot more doable than freaking antimatter, Earth, Jupiter comparisons. Okay, then what? Now, what do we do? So, in effect, get ready for part 2.